Hello, this is Brett from Woodworks. Welcome. In this video, I'm going to be talking about the Opt Lasers PLH3D XT-50 laser head. This is a 6-watt blue diode laser. Opt Lasers makes several different models, as shown in this picture here. They range anywhere from half a watt up to they now make a 45-watt blue diode laser. The XT-50 is my first laser that I'm using on my Avid CNC router. I chose the XT-50 because it has a pretty good resolution to 500 dots per inch resolution, meaning the laser focal point size is fairly small. They do make one laser, the XT-10, which is a much higher resolution at 3100 dots per inch. That is the half a watt laser, which I'm assuming, I've not used that one, but I'm assuming it has enough energy density in that such a small dot size that it can accomplish a lot of good things. But in my case, I was doing wood crafts and other projects, and I wanted something that had a tight enough laser spot to be able to do some good detail, but I also wanted to be able to cut through at least some materials, and the XT-50 will cut through some thin materials, some up to 1/8 inch. More specifically, this video is going to show a characterization of the XT-50 laser head and some of the tests, the cutting test and some engraving tests and some focal tests. I've had my XT-50 for almost 9 months, and each of these tests grew from a need to do different things with the laser over the course since I've had it. And one of the first tests that I discovered needed to be done was a focal length test. Initially, I just assumed that the height gauge that Opt supplies with all of their lasers was going to give me the most accurate, the tightest dot, the best focal length to the material height that I needed. After some playing around with it and after talking with Jim Neeb at Jim Neeb Woodworks, he let me know that that gauge is just an initial kind of a starting point, and each of these lasers needs to be fine-tuned or characterized to know exactly what its focal length is. The first test I performed was the optimum focus test. The test shown here, this is just the graphics used, was run on the laser, and the idea behind this test is to run horizontal and vertical, or X and Y oriented lines with the laser. 0, the set of 3 lines at 0 on each axis, that would be your assumed 0 height, and then each set of lines corresponding to the 5, 10, 15, 20, 25. And the negative of those would be the various heights away from 0 that you would set your laser to run each set of lines. The goal of this test is to see how the laser engraves these lines and then examine the lines to see which ones are the most crisp, less burn around, clearest gaps between the lines. It should be known that the design-in gap between the triple sets of lines is 1/10,000th of an inch. So this was the first test. For clarification, the L plus 0, that's not actually an L, that's actually a simplified graphic of the gauge that Opt provides with their lasers. So it's that gauge height plus 0. So in other words, I set the laser housing directly onto the top of the gauge. The other thing I'll mention here is that since most of my projects are going to be made out of wood, I wanted to run these tests on wood samples. These focal length tests were run on hard maple, had the clearest surface, and would contrast nicely with the engraving darkness of the laser. So after I ran this first run, I noticed there was a lot of haziness around the lines, and so for the next run, I reduced the power down to 50%. As you can see, these lines at 50% seemed a lot cleaner. Let's talk about the results here. You can clearly see that the closer the laser was to the material surface, the darker and more hazy or more close together the lines appeared. The lines are thicker. Up towards the top, you can see it plus 25 thousandths, the very top set of lines. It's looking pretty good. So I used a lighted jeweler's loupe that you can pick up off of Amazon. Again, this was another tip that Jim Neeb gave in his video, and it works pretty good to really get a good look at the lines and how much separation there are. And as you fine tune the optimal focal length, having something to be able to distinguish minor line thickness differences is pretty important. The takeaway from this run is that it appears that my optimal focal length is somewhat above the height of the height gauge that Op provides. So I did some further testing at different zero heights, and you will see that shortly. So here we have another test. I set the zero to be 10 thousandths above the height of the L gauge, and you can see that the more crisp lines are starting to go more towards the zero center set of lines. It still appears, even to the naked eye, it still appears that we're a little shy of the optimal focal length, and examining it through the loupe verified that. It appeared to me that at this point the 20 thousandths or total of 30 thousandths offset from the top of the gauge was going to be the sweet spot. Just to be sure, I ran another test and I bumped it up another 5 thousandths, as you can see. So now we're 15 thousandths above the top of the gauge. This is where I kind of was able to start identifying a little better which ones were the optimal focal length. And you can see I put a mark at the 15 thousandths. So that equates to 30 thousandths above the height gauge. So knowing that, I went ahead and did a final run, again at 50% power, and I zeroed the laser head out at 30 thousandths above the gauge. And even without looking through the loupe, you can tell by the darkness of the lines at the top and bottom, or left and right, depending on which axis you're looking at, that our best, finest lines are right around that zero mark. So from here on out, anything I did with this laser, if I wanted the finest lines possible, I used the height gauge still, but when I zeroed it out at the top of the height gauge, I then added 30 thousandths and re-zeroed Z, and that has worked well from then on. So as I was doing these tests, another thing occurred to me. The farther away from zero that you position your laser, the thicker the lines, and it got me to thinking about future tests, and I'll show some of those here in a bit. But the line width, it may be desired to actually have a thicker line depending on what you're doing. My thought was, especially for things that I wanted to fill, if I wanted to use some block lettering and I wanted to fill the letters in, how would I do that and make it not look like a bunch of lines, but make it look like a continuous filled letter? And so I ran this test again, and I bumped it back up to 100% power, just to sort of get a feel for how the line width changes versus height. This drove me to do some further testing to see what the height versus power and also versus feed speed would do. One last test that I ran, and this was again a recommendation by Jim Neeb in one of his videos. He talked about using these aluminum business cards. They're painted black, and this is one of the only tests that I didn't do on wood. I wanted to see how the laser would perform on a coated metal surface, and it did pretty well. And also this gives you the scale of which these focal tests, the size of these focal tests are. And it was amazing to me how well the numbers were legible, sometimes requiring looking through the loupe to even be able to read what the numbers were, but you can definitely see that they're numbers and you can definitely read them just fine. So it's pretty amazing what the kind of resolution you can get out of the XT-50. I can only imagine what kind of results you could get from the XT-10, which has a factor of 6 times greater DPI than this has. So if anybody out there has the XT-10, I'd be curious to know what kind of results you're getting. I think at that point you're talking about laser printing, like printed circuit boards and things of that nature. So as I mentioned before, the previous test kind of drove me towards a line thickness test, which you'll see next. I wanted to see what kind of line widths I could get with this laser. So I ran a simple test with what you're seeing here at 100% power. The focal test only goes up to 25 thousandths above and below zero. The height of the laser when it's running is not very far off the surface of the work. So to dive deeper, literally deeper into the negative, or getting the laser closer to the material being engraved, didn't seem possible or even helpful to know. So I stuck with the positive z-axis increments you see here. For this test, I wanted to increment that height a little more, just to kind of see what sort of results I would get at much farther away than 25 thousandths. So I ran it at 50 thousandths increments. You can see the results here. It's interesting because at some point there's a drop in energy density at the material surface you're engraving, and therefore the lines start getting dimmer and dimmer. Now, they do get wider and wider. This particular laser, I think I got up to something on the order of 15 thousandths wide or something before I started seeing a degradation. As you can see by my sort of chicken scratch on this test sample, I kind of found the sweet spot. So this is one of those test samples that I keep near the laser just as a storyboard as to, you know, if I want to achieve a wider line, it kind of gives me an idea of how far above the Z0 I need to set the laser. So now I'm going to show the power versus feed speed test. So this test, this was an interesting one, maybe the most interesting one of all the tests that I ran. I wanted to compare power to feed speed to see what the laser would do. The thing to note here is that all of this was done at the new Z equals 0, that is gauge 0 plus 30 thousandths height. What's interesting to me about this, you can see, as you would expect, as the power decreases and the speed increases, the less and less engrave or burn you get. And that makes sense. As you increase in power and decrease in speed, the more engraving you get. And in fact, the engrave at 100% power at 5 inches per minute, it had a depth to it. Now, here's the most interesting, maybe obvious to some part of this, is that if you look at the diagonals of the various powers versus feeds, they're all very similar on a diagonal. So this tells me that if someone was trying to achieve a certain darkness or effect or whatever, that perhaps they can bump up the power and they can also bump up their speed to achieve whichever shade or thickness or depth of engrave you wanted. This is another test sample which I keep handy next to my machine so that I can reference it, and at least it gives me a good starting point for different projects and the effect I want to achieve on each project. So now we're going to move on to the cutting tests. This first test that I ran was on a 0.127 thick piece of hard maple. I ran it at 100% power at 10 inches per minute. The numbers that you see going across the top are the number of passes, the number of times it engraved around each rectangle. When it got to about 6 passes, 7 passes, you start to see, and I'll show the back of this sample here in a minute, but you start to see it kind of cutting through. And then around 8 passes, 7 or 8 passes, is when it really starts to cut through. The pieces start to fall out. Here's the back of that same 127,000 thick piece of maple, and you can see when the laser starts to cut through. You can really see it at the 5 pass rectangle. You can start to see it cutting through. So that's pretty good for this this little laser, in my opinion. So for this next cutting test, I had some 0.197 thick sand ply material floating around the shop. I wanted to try it on some form of plywood. So this is basically a 3-layer plywood, a thin veneer top and bottom with a thicker, softer core. I did the same test as previous, 100% at 10 inches per minute, maximum of 10 passes, and it didn't burn through. So I decided to increase the number of passes, and that's what you see here. 6 passes up to 15 passes. This one had a little bit better results. The pieces still didn't fall out, but it started to appear like it burned through, was burning through the materials. 15 passes took quite a long time at 10 inches per minute. So I didn't want to necessarily keep going on this, but you can see from looking at the backside of this sample that you're starting to see burn through at about 11 passes, and then 15 was a little more. Again, the pieces didn't fall out, so didn't quite achieve what I was hoping for, but not too bad, not too bad. So this next one, again, I ran similar test. This time I went straight for the more passes test. This is a piece of, I don't know if it's considered MDF, it's hardboard composite, a lot of resin in there. So I didn't really have high hopes for this, and it burned to a decent depth, but didn't quite burn through. So, you know, every laser has its limitations. This one, what it has in good detail, it gives up in ability to burn through thicker or harder or more resin filled materials. So the last cutting test I did, I have some veneer floating around the shop, thinner material, and I thought, this laser should be able to cut through that material very well, and it did excellent. I did a test run. I had some blue dyed veneer, and so I cut out the word test, and I did the same to a piece of maple veneer, and when I put the pieces together, they fit wonderfully. So I'll be using this veneer inlay technique on many future projects. I can see lots of uses for this. Everything from making wood grain, different species of wood, pictures, lettering like this, customizing for customers, things of that nature. One last note on this. You can see that the word test was cut out at 100% power at 30 inches per minute. It actually took 2 passes. I'm not sure why it took 2 passes. It should have burned through fairly easily at 1 pass. So I did another test where I just cut some circles above and below the word test at 100%, 10 inches per minute, and it indeed did cut through in 1 pass. So lesson learned is maybe a little slower will result in less passes, and ultimately maybe you save time, maybe you don't, I don't know, but it was interesting all the same. So I mentioned earlier that I was interested in possibly using the laser to fill in like block lettering and things like that. So here's some more tests on that. So like any proud business owner, I was going to need to put my logo on projects that I made, and this was a test to try out how the laser filled in the logo. The first thing I tried was a rastering of the fill of the logo, and as you can see, kind of had a cool effect, but it took a long time, so I stopped it about partway through. So the next test I did was to do just the outline of the logo at 100% power, 25 inches per minute, to see if that setting looked okay. The third logo was my first actual fill attempt other than the rastering, but I forgot to turn on my air assist, so it came out quite burnt. So my fourth attempt, I turned the air assist on. I tried the logo at 100% at 25 inches per minute with a 80% power at 25 inches per minute vertical hatch. And it's starting to look pretty good. Not quite filled in like I wanted, but and still looks a little dark. So I think on this last one I got a lot closer to what I was trying to achieve. I still didn't get quite the fill effect that I wanted. This was run with an outline at 80% at 25 inches per minute, and the hatching was the same as previous, 80% at 25 inches per minute. It looks just a little cleaner given the less power on the outline. So I was still shooting for getting a better fill effect, so these next tests are going to show some fill quality things that I worked on. So this is that same logo. I changed the vertical hatching to concentric offset lines to avoid as much line appearance in the logo to get a better fill quality. Each of these lines is offset 1/10,000th of an inch from the outline. At some point in the video I wanted to show the laser working, so this is that logo being engraved onto a scrap piece of 1/2 inch Baltic birch that I had sitting near the machine. Just for the sake of not boring everyone to tears, I went ahead and sped the video up to 300% of what the machine was running. Feel free to fast forward through this when you get bored. And sorry for the shaky camera work, it really didn't appear that shaky at 100%. I should also mention that the height of the laser was at the new Z0, which is the gauge plus 30 thousandths increase. So here's the finished logo. As you can see when I zoom in, you can still differentiate the laser lines of the fill, and it's amazing how well you can differentiate the lines when the laser is at its smallest dot. This looks okay, but it still wasn't the fill effect that I was looking for. So based on my previous tests, I wanted to try offsetting the Z a little higher to increase the line width and rerun this test. This is at Z equals 0 plus 0.15. I'll spare everyone watching the machine run through this whole logo again, but as I zoom in here, you can see that it has a much better fill effect, almost getting to the point where it looks like a logo brand or something of that nature. And lastly, I would be remiss if I didn't mention a little something about safety. These lasers can do damage to your eyes, so please wear your goggles. I would like to give special thanks to Mr. Jim Neeb at Jim Neeb Woodworks. He definitely helped me out with the setup of this laser, and another shout out to Opt Lasers themselves. They are proving to have some of the best customer service you could expect. They are located overseas in Poland, but that hasn't stopped them from promptly responding to any questions or requests. And another thanks goes to Avid CNC, for without their CNC router setup, I would not have a platform even to mount this laser to do all this fun stuff. Thanks everyone for watching, and if you like what you see, please hit the like button. Subscribe if you want to. I'm going to be putting out more of these videos in the near future.